Morning. Do you know if were there any problems with the technology, or do we start at 9 or 9:05? What is this year the calendar?
I believe it's 9:05.
9:05. Okay.
As far as I can tell from the only problem with it is to show what is projected.
Yeah, it seems not to work.
But other than that, I'm not sure if that'll actually be a problem for your thing.
Hope not. We'll see.
But yeah, other than that, the audio is fine and the video is fine.
Okay. Question is I need to check first. Can I just ask if you can hear me? Can you raise your hand, please? Yeah? Okay. Thank you. Because we had some problems here, so I'm trying to set it up and then I will start it. I think we start normally at 9:05, so I think I still have some minutes. Okay. Yeah, it's good that you're here in case something breaks down. Okay, let me see. And can you see the slides? Can you see the slides? Can you raise your arm if you can see the slides? Okay. I'm not sure. Okay. You should see those as well. The system is extremely slow in reaction, so. Okay, let me do this here and here. That is you, okay. So I think the sound on the other side is actually closed, so I don't want to have a feedback. What do we have here? Okay. Why doesn't it take? This is a nightmare. I cannot move the window. Okay, there we go. Okay, so before I start, if you cannot hear me or see the slides, please let me know by chat. So, can I just ask anybody who can hear me, please raise your hand. Okay. Can everybody see the slides if I move them? Yeah? Can you see the slides? Can I just ask if you can see the slides? Yeah? Because the camera is very, very slow and it seems there is something not working properly here, so I don't know what to do. I will try my best. Okay, so let me start. Very bad. I don't know what's happening. Sorry, I can't get it. It's a total nightmare. Okay, I have a problem here. Just a moment, as usual. Can you see this? Because I cannot see them here. They are somewhere on the other side. But okay, so I hope you can see me and see the slides. I have problems to see you in the moment because there seems to be some technology. I have to report it. I don't know really what happens, but it's really not working well. So I'll try my best. Okay, yeah, so welcome to the second semester of the Magic course. I'm Frank Neumann. I'm giving the course on algebraic topology, and this is actually an introductory course, which means, so it's meant actually in people who are not specializing necessarily in algebraic topology. So I assume a little bit of point set topology, and of course algebra will recall some stuff at the beginning. And if you have not done so, please do register for this course, and also if you plan to do the exam at the end, please do so as well. So this you should do online on the Magic site, and I'm going to check who will be doing the exam. So this will be as usual, to take away home exams, you get some problems and have to solve them and then upload them and so on. So same procedure as always. Okay, so let me start. And what is algebraic topology? So that is the first question you want to ask. So the main idea is actually to study general geometric shapes, for example, topological spaces and maps between them, meaning continuous maps, by algebraic means. So the idea is actually to translate topological geometrical information into algebraic information in order to detect properties of the former one, the topological geometrical shapes. So that's the main idea. And how would you do that? So let me start very philosophically for the moment. And you can think about what is a space. Yeah, space can be very complicated. And for example, one thing you have seen, of course, is a circle, S1, or the torus, donut-shaped figure, or Möbius strips, and so on. And these are kind of sometimes very complicated objects, and to study them, as you've maybe seen in point topology, requires a lot of effort. Sometimes it can be very complicated. Some properties might not exist, and there's a class of objects which have these properties and others, and it's quite hard to detect, for example, when two topological spaces are equal in the sense that they're continuously deformable into each other. So what we will do is we will take all these topological spaces, we group them together in some kind of geometric category of topological spaces. I come to the exact definition later, and we want to study them. Normally, because it is a very big category with a lot of animals which look very exotic and complicated, this category is very hard to study in general. So it is not easy to study it in direct means, for example, to decide if two spaces are equal in the sense that they're continuously deformable into each other. The objects could also be of multi-dimensions, or even have infinitely many dimensions, and our intuition is not much of help. So the idea is actually to see if we can actually translate geometrical properties, at least some of them, into algebraic properties, and then see if we can study them algebraically. Okay, so let me just mention what I mean here. So we'll look at a certain algebraic category in contrast, and then some way of transforming the geometric category into algebraic category. So geometric and topological properties into algebraic properties. But this will mean we have some kind of transformation, or what's called a functor. Again, those things I will describe in detail later. So in the moment I'm just intuitively philosophically here. What do I mean by algebraic category? Well, it means that those objects there actually have an algebraic nature. So this means that there will be, for example, there could be just numbers, vector spaces, groups, modules of a ring, and so on, rings. And this algebraic category is more under our control. We can use all the machinery of algebra and have a lot on our hands, and that's kind of more a linear way of doing things. So the idea then is to obtain information about the geometric objects, or topological objects you want to study, by looking at the image under this functor in the algebraic category. So we'll see what this property means algebraically. So let me just give you a very, very, very trivial, intuitive, basic example to start with. So let's think about a circle, S1, and the two-dimensional disk, D2, for example, in the plane, R2. And we know they are different, We want to somehow distinguish one from another. How could we do that? Well, there's one property you can actually see if you draw the picture. And it is intuitively clear that a two-dimensional square, for example, could be deformed into a two-dimensional cell. However, S1 is not. So what does it mean? And we want to ask whether one could be continuously deformed into each other. Then they're kind of equal in the sense of topology. Now, what's the reason why they're not equal, S1 and D2? Well, if you look at it, S1, of course, has a hole, which must be preserved under continuous deformation, but D2 is solid, and therefore S1 cannot be deformed into it. While, for example, D2 and the sphere are both solid, so they can be, I mean, if you take a sphere surface, I mean, not just a polygon, take the internal part as well, then of course it could be deformed. But if you take S1, then it has kind of hole. So that's not a proof, of course, that's just an intuitive argument. We can see the shapes are different, and they have some different nature. For example, we could take the number of holes. So we could somehow make a translation from the topological or geometrical category into the algebraic category when there's associated to a geometric figure a number of holes in. Of course, then we have to make all this precise, and it might also be difficult. And it turns out this is actually invariant under deformation. Yeah, so this number does not change as the object is being deformed. You can deform a circle, you will still have the hole. You can deform the disk, and it will still have no hole. Yeah, so the invariant is 1 for S1 and 0 for D2. Yeah, and therefore the answer would be it's not deformable into the other. So we basically could decide deformations equivalence by just checking the holes, the number of holes. So that would be a very crude invariant we might think about associating to these geometric shapes. But in fact, this invariant that's the problem if you translate geometrical topological information into algebraic one. You have to find good invariants. And for example, just take a number of holes, even though I haven't really formally defined it, which is also not totally clear what it actually what we mean by that. We have to give a clear definition. This invariant is not quite sufficient yet. Yeah. For example, you could take also S1 and S2. Yeah, the circle and the two-dimensional sphere. Yeah, each one has a hole, but it's intuitively clear the nature of these holes is different. Yeah, and one can still not deform them into each other. So that doesn't work. So we need something more precise. So the basic problem actually of algebraic topology is to find a system of algebraic invariants of topological spaces which in fact would be powerful enough to distinguish different shapes. So that's the aim, the goal. And so we have to construct a good system of algebraic invariants which allow us to distinguish topological spaces, different shapes. Yeah? And of course then this is the first question. You have to define these invariants. On the other hand, we also want to make sure we can compute them. So there are two questions here. Defining good invariants and secondly compute them. Make them computable. And so it should be computable, good computable invariants. So these are two things which come together. You can define any kind of invariants. If you cannot compute them, it's useless. Yeah? And of course, over the decades, from the 30s of last century, people came up with lots of, even before, I think, by Poincaré, came up with lots of invariants of this sort. And we will consider the most basic in this one, namely homotopy and homology groups. So these are the two invariants we want to focus on, and we will see what we can do with them in this introductory course. Of course, it's a vast area, and so I can only start motivating to study homotopy theory, for example, in this course. Okay. Now let's be a bit more precise. So that was just a philosophical run-in. So let's be a bit more precise and see how this interaction between topological, geometric information and algebraic information works. So let's illustrate this as a famous example, famous result, namely Brouwer's fixed point theorem. First stated and proved by Dutch topologist Brouwer in the beginning of the 20th century, when algebraic topology didn't exist. So I will give you an idea of how you can use this idea, namely associating algebraic invariants to topological geometrical information in order to prove such a result like Brouwer's fixed point theorem. So, of course, this is just be a rough outline because I haven't defined all those invariants I'm going to use, and in fact this will be one of the main contents of this course. Yeah, at the end we will have all this in place to see that this proof works. Yeah, so this is a kind of motivation to see that why developing those invariants, especially in the second part, will be useful. So let me just tell you what we want to do. So let's recall the Brouwer fixed point theorem. So you take an n-dimensional disk. Well, you could think of this as a solid ball of radius 1, yeah, having its center at the origin of the Euclidean n space, the n-dimensional real space. Oh, there's a fire alarm, but I think it is just a check. Okay, we have a fire alarm here. I just have to move the... I have to get out of the room, so... okay, stop. Sorry for that. I probably have heard the fire alarm. Okay, so let me start again. We want to look at the following situation. We have an n-dimensional disk, yeah, in the n-dimensional Euclidean real space. And for example, if you prefer to draw a picture, you could take n to be equal to 3, 3-dimensional, or 2, or even 1. This is a very simple case. And now Bauer's fixed point theorem says the following. If you have a continuous self-map from the n-dimensional disk to itself, then this map, continuous self-map, this map always has a fixed point. So it means there is a point on the n disk for which f of x is x. Yeah? So this is what you call the Bauer fixed point theorem. Okay, so numerous proofs of that, and of course this has a lot of applications in analysis. For example, if you want to find solutions of certain equations, in particular differential equations, comes also up in mathematical physics, of course, and financial mathematics. Yeah. So this is a very important result. There's a vast literature on applications of fixed point theorem. This is one of the classical ones. There are, of course, much more sophisticated versions of that as well. Okay, so how would we prove that? Well, if you just try do it by hand, it's not so easy, yeah? But at least one case we can do very easily, which is almost trivial, namely the case n equals 1. You have seen that basically in calculus. So in this case, let me just do the argument in dimension n, for dimension n equals 1. So what you have then, a continuous map from d1 to d1. That's a map from the interval, closed interval minus 1, 1 into itself. Continuous map, yeah? And we can also assume that f of minus 1 is greater than minus 1 and f of 1 is smaller than 1. Yeah, because otherwise there's nothing to prove. You will have a fixed point, yeah? And you might maybe argue, oh, but why I don't assume f of minus 1 is smaller than minus 1 and f of 1 greater than 1. It doesn't matter. You just exchange the roles. You can just take minus f if you want. Yeah? It's a standard trick. Well, to say that f has a fixed point is equivalent of saying that the function g I can define by just taking the difference of f of x and the x value, so f of x minus x, is 0 at some point in the interval minus 1, 1, at some point c in the interval minus 1, 1. Now our assumption on f I just put there implies then that on the boundary we have g of minus 1 is greater than 0, and on the boundary 1 we have g of 1 is smaller than 0. And then we can just use the intermediate value theorem from calculus to find a point inside the interval, in the interval minus 1, 1, for which g of c is equal to 0, and the theorem is proved. So in dimension 1, this is basically just equivalent, if you want, to the intermediate value theorem, or a direct consequence of the intermediate value theorem. But of course, this proof doesn't generalize in higher dimensions. Yeah? So this doesn't work. So we need a new idea. And the new idea now I want to present comes from algebraic topology to illustrate how we actually want to translate topological geometric information into algebraic information. So what can we do? Let's set the stage. Now we have a continuous map from the n disk to itself, a self map, and assume that we can find a map without fixed points. So assume for the moment we have no fixed points. So we want to make some kind of contradiction then, of course, yeah? So prove by contradiction. So assume there exists a continuous map from the continuous self map from the n disk to itself, yeah, without fixed points. We can then take any point in the disk, x, yeah, and we can draw the line between x and f of x. Yeah? Just draw it if you want. Yeah? And well, and such a line is unique, yeah, because f of x is not equal to x. So we always have a line. These 2 points, f of x and x, are different. So we also have a unique line through these 2 points, f of x and x. Now, if you take this line, the straight line, this will intersect the boundary, which is the n-1 sphere of the n, in precisely 2 points. And then take the one that's closer to x than to f of x. And we denote this point by capital I of x. This will define me a new map, a continuous map, from dn to its boundary, Sn-1, and I call it, yeah, x goes to I of x to this point. And I can also call this map just I, capital I. And if you take the point I of x restricted to the boundary as n minus 1, if you just restrict this map to the boundary as n minus 1, then of course it's just identity map on as n minus 1. Yeah? If you have a point there already, then it's just maps it to itself. Right, so let's make a definition which is relevant here. So assume you have a subset y in X, then we call a map from F to X to Y. So in fact we have topological space in the subspace, and we have a continuous map from X to Y, but we can also define it for normal functions of sets. So a map is called the retraction of X onto Y if F restricted to Y is the identity map on Y. Then Y is called the retract of X. So if you have a map from X to Y, and Y is a subset in X, and if you restrict to Y, you get identity map, then we call a Y a retract of X. Okay, so what we have basically done now is we have, under the assumption that the continuous map from Dn to Dn has no fixed points, we have constructed a retraction of Dn onto its boundary Sn minus 1. And what we will do now is we will show that this is impossible. We will show that such a retraction cannot exist. This is the main point. And then we know there cannot be a continuous map without fixed points. So how will we do this? Well, what we will do is, in the course, we will construct them. So is the following. We want to show that they exist to any topological space X, for which the n cell and its boundary, the n minus 1 sphere, are examples, which we care about here in this application. To any such a topological space, general topological space, you will associate a sequence of abelian groups. So for each n equals 0, 1, 2, and so on, we will have an abelian group, Hn of x. It depends on n and on x. Whatever it is, I will define that. And this is called what we call the homology groups. And they should have some properties. Namely, they should behave what we will later see as functorial with respect to topological information to algebraic information. So what I've done is I've started with the topological category, geometric category of topological spaces, and I associate to each object there a sequence of abelian groups. And also we want that to each continuous map from X to Y, we get a corresponding homomorphism of abelian groups from Hn of X into Hn of Y for each n. So if you want, it's a sequence. We associate to each continuous map a sequence of homomorphism of abelian groups. And it should behave well with respect to composition. So if you have a composition of two continuous maps, then the association should give you a composition of those group homomorphisms. So this is kind of what we call functorial behavior. We'll make all this precise. And then I said these invariants should be computable. In fact, they should have very special values. If you take the n-disk, then the homology group should be all 0 for I greater than 0, and any n. So this calculation, we have to construct these invariants, and we have to show that this has this value for these particular spaces. And also, we want special values for the n-sphere. Namely, it's exactly for Hn of the n-sphere, we will have the integers, the group of integers. So these are calculations I will have to do after I have defined those invariants formally. But assuming that we can do that, and that's what I'm going to show you during this course, assuming we can do that, then of course we can reformulate on the topological problem of finding of having a map without fixed points in algebraic terms. So we can really deduce Bauer's fixed point theorem very elementary from these three properties. Now, of course, the work which gets in here comes in the construction of this invariant and its functorial behavior. And that's what algebraic topology does, constructing invariants in a functorial way, from the topological category to some algebraic category. In this case, from topological spaces to abelian groups and group homomorphisms. In fact, you will see later that this correspondence, which associates to a topological space the sequence of abelian groups, is in fact a functor, or better to say a collection of functors, because we get one for each I, for each integer I. from the geometric category of topological spaces to the algebraic category of abelian groups and group homomorphisms. Okay, now let's do the translation in our situation, taking this for granted, and complete the proof of Brouwer's fixed point theorem. So we have also another map. We have this map, this capital map I, which I have defined just now from Dn to Sn-1. But we also have an obvious inclusion map, yeah, by just taking the boundary into Dn. No? We have the inclusion map. Yeah? It's just the identity again on Sn-1. And if you take the composition of the two maps, then you get the identity map. Yeah? So the composition is just the identity map. Now, if you have, what do we have now? We have three spaces and two continuous maps among them. Now, if you assume that we can do what we want to do, we have an association of a sequence of abelian groups to it and group homomorphism, we will get a sequence of group homomorphism of this form. Yeah, and I do this for only for the index n-1, because that's all what I need. So these three spaces and these two continuous maps, I have associated now the n-1 homology group, so I get the sequence of group homomorphisms and abelian groups in this form, Hm-1 Sn-1 goes to Hm-1 Dn and goes to Hm-1 Sn-1. Yeah, and if we start with the composition above, these were very special maps, and the composition was identity map, and it should reflect those properties of composition, then we should get the identity homomorphism here. Yeah, and we know what the value of Hn-1 Sn-1 will be, so that's what we will prove. This will be Z. Yeah? Okay, so on the left and right, we get the integers. And we also know what the homology of the disk was. Remember that we want that it is all 0, if n is greater than 1. So Hm-1 dn is 0, if n is greater than 1. And therefore, our sequence of abelian groups and group homomorphism just simplifies to this one. Z goes to 0, trivial group goes to Z. And there's no way. This composition has to be 0, right? There's no other way. And it's not the identity on Z. So we actually get a contradiction. Yeah? Under the assumption that we can construct a continuous map, self-map from Dn to Dn without fixed points, we get a contradiction here. Yeah? So this contradiction then proves our theorem. So you see, the proof of Brouwer's fixed point theorem is just one page, basically. Yeah? It's very easy by just translating the topological information into algebraic information. So what we have to do is, what I have to do is, in this course, I have to make sure I construct these invariants, yeah, with those properties, yeah, functorial properties, and which allow for clear computations so that we know the value on the disk and the n-sphere in this way. Yeah, and then the proof is done. So this is what we have to do now, filling in this gap. But assuming this, you see, Brouwer's fixed point theorem is a direct consequence of this. Okay. Yeah, so in order to do so, let me start with some recollections of things so that we know what we're talking about. I'll do this very quick. So I need some background from topology, algebra, and category theory, and the rest I will then develop from scratch. So I hope you have seen this. So it's just a collection. I will just record it here. So let's start with algebra. Yeah, so all of you hopefully know what a group is. Yeah, so a group is a set together with a map multiplication such that you have some axioms. It's associative. You can find a two-sided unit, yeah, an element E and G such that E times G is G times E is G for any G and G. And for any G and G, you have an inverse, two-sided inverse elements, so meaning that you find for each G and G minus 1 in G such that G times G minus 1 is G minus 1 G is E. Yeah, so that's a group. And if the multiplication is also commutative, then we call the whole thing an abelian group. Yeah, and normally for abelian group, I will also follow the convention that you write it as G plus H in additive versions. Yeah? Okay. Let me also remind you on some other important things. So a subgroup is just a subset which contains the unit, and together with any element contains its inverse and is closed under multiplication in G. Yeah? So closed under the algebraic structure. And we call a subgroup normal if for any G in G and H in H, the element G, H, G minus 1, so the element H conjugated with G also belongs to H. Yeah, and then we can define for a group G and element G in G, we can, and in the subgroup H we can always define the left coset, so that's a collection of elements of the form GH, where H is an H. Yeah, these are the left cosets. Of course we have the right cosets, also collection of elements of the form HG, where H and H. And if the subgroup of course is normal, then the collections of left and right cosets coincides, and both are called the quotient of G by H. So we get a group, the quotient group. Yeah, and then, as I said, we want to look at the category, so we have objects and morphisms, and I will make all this precise, so we call that as well. But it means that we have to talk about maps between groups, so for two groups G and H, a homomorphism of groups is just a map of sets such that it respects the multiplication, so FG times H is F of G times F of H for any G in H and G. Then we have the notion of a kernel, yeah, the set of elements in G which map to the neutral element in H. It's easy to see that this is a normal subgroup of G. We have then another important construction is the image of homomorphism, by IMF, yeah, so this is a set of all elements in H which having a non-empty preimage under F, so everything which got hit from an element of G in H. Now that is again a subgroup of H. And then we have the normal notion, the homomorphism is an epi, or onto if the image of F is H, and it's a monomorphism if the kernel is trivial, it's just a neutral element in G, and a homomorphism which is both mono and epi is called an isomorphism. And it's sometimes good to give a different equivalent characterization of isomorphism. It's easy to show that an isomorphism from two groups G to H admits an inverse isomorphism F minus H, which goes in the other direction H to G, such that F composed F minus 1 is identity on H, and F minus 1 composed F is identity of J. So we could use this also as a definition. This is kind of a categorical definition of an isomorphism in the category of groups. Yeah? This is actually the better definition, kind of. Okay? And then, the basic theorem, homomorphism theorem from group theory, says that the image of F is always isomorphic to the quotient group G modulo kernel of F. So G modulo kernel of F is isomorphic to the image of F. So this describes basically what happens for group homomorphism. Yeah, I'm sure you know all this. I just wanted to list it because that's basically the properties we need. Now, going a step further, still in algebra, we would like to introduce some notions which you might not have seen. I hope you did, but let me just recall it, namely the notion of an exact sequence. This is really important. It's an important working tool in algebraic topology. It comes up all the time. Okay, so what do I mean by a sequence of abelian groups and homomorphisms? Well, it's obvious. It's a sequence of abelian groups and group homomorphisms, right? So I could go to the left infinite terms and to the right infinite terms, yeah, and I have indexed here, so I have infinitely many abelian groups, say indexed with the integers here. By the way, I could change it. I could just index it with the natural numbers. Maybe I just take a finite subset of the natural numbers, yeah, it's kind of bounded to both sides. I could also take other index sets, I don't care. This is what we will mostly need, and but I'm just saying you can do it more generally. And then we have group homomorphisms between them, yeah, which I have indexed depending on where they go, where they start. No? Okay. Yeah, this is a sequence of abelian groups and homomorphisms. And now we call it exact if at each position, at each abelian group, we have that the kernel of Dn is the image of Dn plus 1. So the kernel of the homomorphism which goes out is equal to the image of the morphism which goes in. And we do this at each position. Then we call this sequence exact. If it's only exact at one position, we call it exact at AI, for example. I didn't write it here. Yeah? So an exact sequence means it's exact at each position, yeah? Meaning that the kernel is equal to the image. Let's consider some special case of this definition to see what it actually does in simple cases. Well, here's the most simple case. Assume that all groups AI would be trivial, the trivial group, besides AN. But in that case, the exactness of this sequence, so they're all zeros besides AN, it means, of course, that AN has to be 0 as well. There's no chance, yeah? Because the image of the ingoing map is 0, and the kernel is everything. So that means AN is 0. Okay. Let's take a slightly more complicated case where we have a sequence which only consists of two non-trivial groups, neighboring groups. Yeah, so the neighbor here. So again, we have an and an minus 1, and then, well, obviously what it means is, it means nothing else that the homomorphism hn to hn minus 1 is an isomorphism, yeah? And you can check this. It's injective and surjective. Yeah? Because take the image of this is the kernel of this, all of this is in the kernel, the image is everything then. And you can see that the kernel is 0, because if you think of where the image of 0 goes, it's 0. So that's an isomorphism, you can check this. Okay. Now let's take one more case, which is a bit more interesting. In fact, namely the first non-trivial case where this actually comes in is when you have three consecutive groups which are non-trivial and then zeros. So I only write normally those zeros which are close to the non-trivial stuff. The rest I can just ignore. There will be a lot of zeros to the left or right. I just don't write them anymore. Yeah? Okay, so assume we have a sequence of this form which is exact. Then we call this a short exact sequence, for obvious reason. And what does it mean, exactness in this case? Well, it means, first of all, that the homomorphism, group homomorphism from an to an minus 1 is an epimorphism, yeah, because there's a 0 on the left. And the homomorphism from an plus 1 to an is a monomorphism, yeah? It's a 0 on the right. So we could consider an plus 1 actually as a subgroup of an. We can identify an plus 1 as a subgroup of an if I have it. You can always do this if you have a monomorphism, right? And what's the kernel of the homomorphism from an to an minus 1? That's precisely this subgroup an plus 1. So, the short exact sequence gives rise to an isomorphism using the group homomorphism theorem, namely an minus 1 is isomorphic to an modulo an plus 1, this quotient group. So that's basically the information of a short exact sequence. Okay. Now let's slightly generalize this. And slightly generalizing the concept of a exact sequence is the concept of a complex of a building group. Okay, what is that? So again, we have a sequence of a building groups and group homomorphisms. Again, it could be infinite. And again, in this case, I index everything as integers. Now this is called a chain complex, normally written A, comma D. Yeah, is the composition of any two consecutive homomorphisms is 0. So you compose two consecutive homomorphisms and you get the 0 map. So Dn composed Dn plus 1 is 0. That's slightly weaker than exactness. Huh? You can think why. Yeah? I'll leave it to you. It's very easy to see. So show that an exact sequence is a complex. It's almost trivial, just by definition. Now, and this means that in particular, if you have a complex which is exact, that's somehow considered trivial in some sense. Yeah? You'll see later why we call this trivial. So somehow a complex measures the non-triviality of a complex, so of not being exact at a position. Yeah? So because if it would be exact, then we know that we have this isomorphism, and we get something trivial. But if it's not exact, we can always build the quotient kernel. Yeah? So we can always build this quotient kernel dn modulo the image of dn plus 1. Yeah? For an exact sequence, this will be trivial, yeah? Because it says that the kernel of dn is equal to image of dn plus 1. So we get the trivial group. But in this general case of a complex, we only have that dn composed dn plus 1 is 0, which means that the image of dn plus 1 lies inside the kernel of dn. Yeah? It's a subgroup. And therefore we can build the quotient group. Yeah? These are all our building groups. So we can build the quotient group, kernel dn modulo image of dn plus 1, and we call this the n's homology group, h and a comma d of the complex, no? At the position n. Yeah? So we can see therefore that an exact sequence has its homology equal to 0 in all positions, so in all degrees I and z. So somehow homology is actually a measurement for a complex not being exact at a certain position. Whenever the homology is 0, we know at this position in my sequence we will have exactness, yeah? And otherwise not. Yeah? So homology measures the non-triviality of a complex, non-exactness of a complex at a position. Now, so this is already the definition of homology. Of course, this is purely algebraic, and I haven't made the link between the geometric category, topological spaces, and this. So we have to construct, somehow a complex coming out of topology. And this will be the hard work. And then we can just use algebra to construct these homology groups. This will be what's called the single homology groups, which we'll introduce later in the course. Okay, so far so good about background from algebra. Let me now also recall some basic stuff from point set or general topology, which I will need. I assume that you have seen the topology course, so if not, let me just put together the things I basically will need so you have them on record. Okay, so what's a topology? Well, you take a set as an underlying set and you add some extra structure, like with a group, no? You start with a set and you add some algebraic structure. Now what's a topology? Well, it's basically a collection of subsets which satisfy certain axioms, so the empty set in X is in there. For any collection of sets Ui in tau, the union also belongs to tau. If you have two sets, U and V, or finally many, belong to tau, then the intersection will also belong to tau, intersection of finally many. Unions of any will belong, and intersection finally many. Yeah? If you have these three axioms, then a set X with a topology tau is then called a topological space. Normally, if you want to be precise, you write X together with a topology because you can define different topologies on the underlying set. Yeah? So you've probably seen, especially for finite sets and so on. Right, and then we give a name to those subsets which describe the topology. So a subset in tau will be also called an open set in X, and we have a concept of closed set by just taking the complement of that. Also important is the notion of a neighborhood of a point in X. So that's an open set such that the point is inside that open set. Now you can surround the point in this way by an open set. It's a neighborhood. And then we can talk about an interior point of a set Y in X, a subset Y in X. Well, that's a point Y in Y such that Y contains a neighborhood of Y. You can always surround it with an open set. Yeah. You have seen many examples of topological spaces, many coming up in analysis. Normally, basic example is a real line, R1, and the topology here is given specified by the collection of open sets in the usual sense of R1. That is a countable union. So that is countable unions of open intervals you get in order to define topology. You can also define them by a certain basis. You just have to say what open sets. I will not write it down again, but that's basically how you create a topology. You can generalize this to n-dimensional real space, or Euclidean space Rn. Topology is given by a collection of usual open sets in Rn. So this comes out from analysis. But we also have what's called the discrete topology, which is defined by declaring all subsets to be open. That's an extreme case. And then an opposite extreme is what sometimes called the anti-discrete topology, in where you declare the open sets only to be X and the empty set and nothing else. So these are the two extremes, and any other topology will be in between there. So you can build a lot of topologies depending on what nature your space will be. Okay, and then another important issue is, of course, how to build new topological spaces out of a given one, and there are many procedures to do so. Of course, if you have a topological space and a subset, then we can make the subset into a topological space by taking the subspace topology, by declaring the open set the sets of the form U intersecting Y, where U is open in X. This will define me then open sets in Y, and therefore give me a topological structure, a topology on Y. So this is then called a subspace. Another very important example which comes up is the other extreme. So we have normally sub and quotient constructions. So the other one is a quotient space given by some equivalence relation. So equivalence relation on the set X is just a subset of the Cartesian product such that you have three axioms. It's reflexive. If the pair X, X is in R for any X. So we declare that the pair X, X is in R for any X. It's symmetric. If X, Y is in R, then also Y, X is in R, and transitive. So if X, Y and Y, Z, these two pairs are in R, then also X, Z is in R. Normally we write X tilde Y if X, Y is in R. And this means that X is equivalent to Y. So if you have this equivalence relation between the 2 points, 2 elements, X and Y. Then we can talk about the equivalence class of X. the element x in x, so it's a set of all elements in x which are equivalent to x. No? And it's easy to see that two equivalence classes are not equal, then they are disjoint, and any element of x belongs to a unique equivalence class, yeah, namely exactly that one bracket x. Yeah, and normally then we introduce a notation for the set of equivalence classes is written as x mod r. Yeah? So this is a quotient of x by the equivalence relation of r, and we get also a surjective map for free from x to this quotient x mod r, which maps x to its equivalence class x. Yeah, and then we want, so this is just for sets, but then we want to do this in the topological spaces. So basically what we can do is we can define a topology on this quotient. So we have an equivalence relation on the topological space now. We take its quotient as a set from this equivalence relation, but then we have to declare a topology, and this is what we call the quotient topology. So if you have a topology on X, we can induce one and the quotient space in the same way as we induce something on the subspace, on the subset. Yeah? But we have to be a bit more careful here. So what is the topology of the quotient space coming from an equivalence relation? So we declare all sets, all subsets in X mod R open if the preimage of U is open in my topology X. Yeah, basically this enforces this quotient map, which comes from an equivalence relation, to be a continuous map. No? Yeah, and very important example of a quotient space is it's a contraction of a subspace. So assume we have a topological space X and a subset Y in X, then we can define a simple equivalence relation on X by just declaring 2 points X1 and X2 in X equivalent if both of them are in Y. Yeah, and then we get the resulting set of equivalence classes that's denoted normally by X mod Y, and basically you identify everything which is in Y to a point. Yeah? You mod out Y in some sense. Yeah, so this is the most important example. For example, if you take this construction and apply it to the unit interval, so X is 0, 1, the unit interval with its usual topology, let's say in R1, induced, and Y be the boundary, so these are the two endpoints, 0 and 1. Yeah, then if you take the quotient space X mod Y, then what you get is in fact the unit circle as 1. So that's a way of constructing the unit circle, but just identifying the endpoints of the interval. Oops. Yeah. Yeah, another way, so subspaces, quotient spaces. The simplest way to build a new topological space is by just taking the disjoint union. So assume we have some index set, not necessarily finite, of a collection of topological spaces, indexed by a set I, and then you just take as open sets just the disjoint unions of open sets in Xi. This gives me a way of just constructing a new topological space. And how much time do I have left? Yeah, maybe 5 more minutes. Another important construction is, of course, then the product of two topological spaces. Yeah, so what we can do is, take the underlying sets, X and Y, of two topological spaces, X and Y, and take the Cartesian product, so the set of pairs. And how we define a topology on that, that's a bit more involved. It's probably have seen when you do pointed topology, so let me just basically recall what you do is, of course, if U is an open set in X, and V is an open set in Y, then you want that the product, the Cartesian product, is an open set in X cross Y. But this is not enough. You can check it for the product of 0, 1 with itself. And we have to be a bit more refined in allowing what open sets should be. And then we say that the subset W in the Cartesian product is open if W is a union, possibly infinite, of subsets in X cross Y of the form U cross V, where U in X and V is in Y. Yeah? So this is what you want to do. And this gives me the right product topology. Yeah, this is for two spaces, but of course we could also define a product of a collection, possible infinite of topological spaces. We have to be a bit careful with that, but in principle you can do that. And then you can take the product topology on Xi. Yeah, so this is just what I wanted to recall from the construction, from pointed topology on the construction of new topological spaces out of old ones. Well, these are spaces, these are the objects in this topological category. I haven't defined it yet, but we also need maps. What are the maps? Well, the central notion of pointed topology, general topology, is that of a continuous map between topological spaces. Just recall, if you have two topological spaces, a map of the underlying sets is then continuous if any open set U and Y in the preimage, F minus 1 of U is open in X. Now that's the definition, the general definition of continuity between topological spaces, which generalizes all the notions you have seen in calculus and analysis. For example, it's easy to check that this generalizes a classical notion you normally define with, with neighborhoods, epsilon delta definition. Yeah? If you have never done this, never seen this, try it out to show that this, for topological space R with its usual topology, the two notions of continuity, epsilon delta and the one-ness topological space are equivalent. Examples of continuous maps, yeah, coming back to the constructions I have introduced. If you have a subspace of a topological space Y with a subspace topology, then the inclusion map is continuous by definition. The same I have just said, that if you take the quotient of a topological space by an equivalence relation, it comes with a projection map, and by definition of the quotient topology, you will see that this projection map is then continuous. Inclusion maps from each topological space Xi into the disjoint union will be all continuous, and the same with the projection maps, which go into the factor into the factors of the product, from the product of Xi into Xi are continuous. Yeah, and how are these projection map defined? Well, if you have such a sequence of points, could be infinite. Yeah, then you just map it to the east component. So that's what you do. This gives me a continuous map. So these are the basic examples of continuous maps, which corresponds to those constructions of new spaces out of old ones. As we have a notion of isomorphisms in algebra between groups, we have a similar thing in topology, and we declare a continuous map between topological spaces a homeomorphism. This is the notion of isomorphism in topology between topological spaces. If F is continuous, that's important, bijective, and the inverse map is also continuous. Remember, this is really important to declare that the inverse map is continuous. You will get it if you have a bijection, you have an inverse map, but it also has to be continuous. It's not automatic. In fact, it is possible for a map to be continuous and bijective, but not being a homomorphism. For example, you could take the semi-open segment X is the half-open interval 0, 1, closed at 0 and half open at 1 on the real line. There's a subspace in R. Then, of course, there's a continuous map from X to the circle. And basically, what does it do? It brings the two ends 0, 1 closer to each other until they coalesce. That map is bijective, but the inverse map would involve tearing the circle, and so cannot be continuous. So I've never seen this work out in the details. You find this in any general topology book. But you have to be careful, and you have to declare the inverse map to be continuous. By the way, here's another trivial example why it's important to care about. You can take the map x delta to x, where x delta is this discrete topology coincide with x as a set, but it's applied with a discrete topology. So you just take the underlying set, as you take it any topological space, and you take the underlying set and you take the discrete topology. And then this map is just a tautological identity on the level of sets. It is continuous and one-to-one, but it cannot be a homomorphism unless the topology on X will also be the discrete one. Okay. Well, informally speaking, you can say that two spaces are homeomorphic if they have somehow the same number of open sets. Of course, this doesn't make any sense, but this is the intuition about that. And if you look at these examples of this above of this space 0, 1, then it somehow has more open sets than S1. If you take the discrete set, it has more open sets than X. X is not a discrete set. So homomorphism should take care about the topology. It should be really an isomorphism with respect to that. Okay, I think I should stop here now. Let me just mention, topological space is also called connected if it cannot be represented as a union of two non-empty open sets V and U, which have intersection and being empty. So I will continue with that. Let me just mention there's a related notion, that of path connectedness, which is more intuitive in some sense. A path in topological space is a continuous map from the unit interval as a parameter space into X, and the endpoints gamma of 0 is A and gamma of 1 is B. Let's call them A and B. Then we say that A and B, if you can find such a path, we then say that A and B are connected by a path gamma, and the space path connected if any 2 points in X can be connected by a path. So these are the two notions of connectedness which we will meet during this course also. and I will continue with that on Thursday. So I hope the technology worked and you could hear me and see the slides. I will put them also up. I also put up hands out where you have the slides without the breaks, so you just get the slides, each with the definitions. Yeah. And later I will also put everything together as lecture notes towards the end, and I'll put this up. Okay, so thanks for listening. And please remember to register for the course if you haven't done it yet. Thank you.